Well, if my, I'm going to go ahead and write my recursive first. Remember, for recursive, you have to state your first starting term. So we have a sub 1 equals 7. And then our actual recursive formula is going to be the term I want is the term before it plus 3. All right, explicit. I'm going to go straight to the short version of the explicit. And our short version is going to be a sub n is going to equal our common difference, which is 3 times n. And we're going to add c, where c is our first term minus our common difference. So in this case, it'd be 7 minus 3, so it'd be plus 4. As soon as I write it, I'm just going to double check. My first term should be 7. Well, 3 times 1 is 3, plus 4 is 7. Let's check one more. My second term is supposed to be 10, so I plug a 2 in here. 3 times 2 is 6, plus 4 is going to be 10. We're good. That is the explicit formula for it. All right, what questions do we have from the homework? Yes? 13. All right, number 13 says the first two terms of the arithmetic sequence are given. Find the missing term. So we know it's arithmetic, right? We know it's arithmetic, so that means that the difference between 3 and 13 is going to be plus 10. So that means my next sequence, a sub 3, is going to be 23, 33, so on and so forth. Not the most effective way, because I want to get all the way to 9. So you could count by tens. Or we could say, well, a sub 9 is just going to equal either the first or second term, doesn't matter. Let's just say a sub 1. Plus, we got to count how many steps are between 1 and 9, and that's going to be 8 steps. So it'd be 8 times our common difference because it's 8 steps. Well, I know 1, so we a sub 9 is going to equal that 3 plus 8 times our d, which is 10, which is 83. Either way will get you the same answer. The problem is what if I say, what if it's a weird one like 2.5, and I give you find me a sub 100? Are you really going to want to go through every single step? Probably not. So either you do this formula or you actually write the explicit formula that we did yesterday, that you could just say, okay, well that's just 10 times d plus or minus 7 would be the other thing we could do. Okay, other questions? Is that good though? Okay. So as soon as I say it's arithmetic, you know that if this is plus 10, the next one has to be plus 10. That's the only way it's arithmetic. Okay, then on to today's lesson. Today's lesson, we're going to talk about series and sigma notation. We're going to start by talking about what a series is. So a series is a sequence, right? We take a sequence, and all we're going to do is we're going to add every single term in that sequence. So that's why it says a series is the indicated sum of all the terms in the sequence. We have two types of series, two major types of series. So I'm going to put a little branch. We have one called a finite series. So we have finite series. I guess I'll put series as well. A finite series is just, let's say we have 1 plus 3 plus 5 plus 7. That is a finite series because it ends. It has a starting point 1 and it ends at 7. So I can easily add those up. I can say it's just equals 16. On the other end of the spectrum, we're going to have infinite series. Just like the name implies, these are going to go on forever and ever and ever. So I'd have 1 plus 3 plus 5 plus 7, but then that we would keep adding and adding and adding. So that's going to be an infinite series. A finite series, we're going to learn how to add all these up tomorrow very quickly. Infinite series, you can actually add them up, but it has to be a certain kind of infinite series. And that's going to be more of like a calculus-based calculation. So you should get that next year. But this year we're going to get this down pat. Okay, when noting a series, I don't want to keep, every single time I write a series, I don't want to have to write the whole thing out. Just like with our sequences, I want to come up with an equation or something that can symbolize what I'm saying, adding up all of the elements. And that's where sigma notation comes in. Sigma notation, if we have any sequence, a sub 1, a sub 2, a sub 3, and we want to add all those terms up, we're just going to use a sigma notation, and we're going to put our formula as a sub n. And note that we have n equals 1 and a k above it. That n equals 1 is going to be our starting point. That's where we start. So in this example, we'd start at n equals 1. And we're going to end when we get to k. That's going to be our end point. That n equals 1 is sometimes called our index as well. So it's our start point. It's also called our index. Because I can actually change that 1 to a different number and keep everything the same. So the summation will be the exact same. So this start point is somewhat arbitrary, and we'll see some examples later on. All right, just a couple examples of our sigma notation. So I'm going to start at 1, and I'm going to end at 4. So all that's saying is we're going to start by plugging 1 in for n. So I plug 1 in for n, and I square it. That's my start, plugging 1 in for n. Then we're going to add to it 2 squared. Then I'm going to add 3 squared. Then I'm going to add 4. Squared. Well, that's just going to be 1 squared is 1. So we have 1 plus 4 plus 9 plus 16. Well, that's just going to equal 30. This is called a partial sum. Because I gave ourselves a sequence and I called it n squared. But I didn't take the entire sequence, I just took part of it. I took between 1 and 4 and I added them all up. So this starting value is just our first term. Alright, it's just plugging 1 in for whatever n or whatever variable we have. This fourth one is my fourth term. So my answer is not going to be 4, it's just going to be when I plug in 4. This also says that I have 4 terms. If I start at 1 and go through 4, I should have 4 terms. We have 1, 2, 3, 4. I have 4 terms. Why it's important to recognize that is because our next example goes to infinity. So we have an infinite number of things to add. So we are definitely not going to add them all up. Instead, we're just going to start at 1 like we did over there. So we have 1 squared. Plus, then we'll have 2 squared. Plus 3 squared. And that's as far as I'm going to go because we're just going to say it's plus dot dot dot. So this one would be an infinite series. And we just state it as an infinite series. So we have a partial sum and we have an infinite series. Only sometimes you call it an infinite sum. Most of the time we just call it an infinite series. Okay. We're supposed to write the following expanded form and find the value. Alright, so that left one. I am going to go from the third term basically to the seventh term. So in other words, where does n equal 3, n equals 4, n equals 5, n equals 6, and n equals 7? That's going to be my pattern. So we're going to say this equals, well, we'll have 2 times 3, because that's my starting value, minus 1. Then we're going to add 2 times 4. So 3, 4. Then we'll go up to 5 plus 2 times 5. I want to keep the pattern the same. 5 minus 1. I got to go down to the next row. Good thing we just have 2 more to do. So we'll have 2 times 6 minus 1 plus 2 times 7 minus 1. So all I did is I replaced all of my n values with 3, 4, 5, 6, 7. I know to start at 3 because I have I equals 3. I know to end at 7 because my top is 7. It doesn't matter how many n's I have. If this would have been 2n minus 1 times n to the nth power. Every n would replace with 3. Every n would then be replaced with 4, 5, 6, 7, and so forth. All right, let's go ahead and get the partial sum. Well, the good thing about this is generally these have nice patterns. So if I have 2 times 3 minus 1, I'm going to have 5. Plus 2 times 4 minus 1 is 7. 2 times 5 minus 1 is 9. And I'm going to notice that we're just adding 2 to each of these. 5 to 7 is 2. 7 to 9 is 2. So my next one is probably 11. And my last one's going to be 13. It's good to recognize that pattern, because if I said go from 3 to 15 or something, I don't want to have to write all this out. And if I realize this pattern, I would just go, well, I have 15 terms, so that would be 1, 2, 3, 4, and I would just count to 15 using this pattern. All right, well, this is just going to be, well, 13 plus 7 is 20. 9 plus 11 is 20 as well, so we end up with 45. Our next one's a little different. I don't have any n's, I just have a 4. It just says 4 on it. I'm going to tell you right now our answer is not 4. What do you got, Jeffrey? 20. It's going to be 20. Yeah, how did you do that? What was that?
4 times 5.
4 times 5. So Jeffrey just did 4 times 5. I'm going to write it all out. So it's 4 times 5 because we have... Okay, for our next one, we have 1 over 5 minus 1 over 7 plus 1 over 9 minus 1 over 11 plus 1 over 13. Now, if you get in your head and you're actually constantly thinking about what am I going to add and then subtract, add, subtract, don't do that. The first thing you're going to do whenever you see adding and subtracting alternating between the two is you're going to immediately go to yourself, okay, it's alternating between negative and positive, so that means I need to do something first. I want to take care of that negative and positive first. In order to do that, I have to do something with negative 1. I have to raise it to some power, yeah. N minus 1. Perfect. I'm going to pretend like I didn't recognize it's n minus 1 and I just picked n. Alright, I just picked n. It's a mistake. It's a mistake, and I'm just going to check to make sure it's a mistake. My first term needs to be positive. Negative 1 to the n is negative, so this wouldn't work. But n to the negative 1 would definitely work. Real quick, would n plus 3 work? Would n plus 3 work? Well, let's think, my first term should be positive, right? So if I plug a 1 in for this, what's 1 plus 3? I think it's 4. What's negative 1 to the 4th power? Is it positive or negative? Positive. Does n plus 3 work? Yes, it does. Would n to the 11th work? Yeah. So all of these are viable options for this, but more traditionally we either use n plus 1, or n minus 1. And since Mike already gave us n minus 1, I check to make sure it works. First term, 1 minus 1 is 0. Makes it positive. We're good. Okay? So whatever you pick for this, just make sure it works for the first one. If the first one needs to be negative, make sure when you plug a 1 in, it's negative. If it's positive, make sure when you plug a 1 in, it stays positive. Okay? Does that make sense? Okay. So as soon as I take care of this positive, negative, all these negatives basically fall out. We think they're all positive. All right? In your head, think of all of these being as positive numbers. So that means to get from 5 to 7, I would add 2. To get from 7 to 9, I would add 2. 9 to 11, add 2. 11 to 13, I would add 2. So it's arithmetic. And so we're going to have a sub n. My top stayed the same, so it's still 1 all the way across. My common difference is 2, right? My common difference equals 2. My first term equals 1 over 5. All right, so we have 2, 1 over 5. So our formula is going to be our difference times n, and it's going to be plus our c. And our c is going to be our first term minus 2. So our first term is 1 over 5. Minus 10 over 5 is going to turn into a negative 9 over 5. And maybe if you're stuck on that, maybe make a little note to yourself that this was, in fact, 1 over 5 minus 2. All right, we have everything we need. Now I can write in sigma notation. So sigma notation, we write our E. And I'm going to put I equals 1. Where am I going to stop? Who knows where I'm going to stop on this one? So I have my start, Mike? 5, yep. And I'm going to go ahead and show both ways we could write this. We could write it as either negative 1 to the n minus 1 times 1 over 2n minus 9 over 5. Or we could just shoot that guy on top. Not actually shoot a guy on top. We're going to move it to the top. N minus 1, and it'll be over 2n minus 9 over 5. Either one of those is acceptable answers. All right, next one is an infinite series. And if we notice, it's not going to be arithmetic. We should always do that check where we have common bases. You can always do that check to see if you can make common bases, and it doesn't make sense as infinite because we don't know what all these other bases are going to be. So it's not going to be arithmetic. But something should scream out to us when I see 4, 9, 16, 25, 36, 49, 64, 81, 121. Yeah, they're all squares, right? They're all squares. So I'm going to go ahead and rewrite this as 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus ... So these types of problems are ones you just have to see. All right, it's going to make your life a lot easier. Notice perfect squares. Well, that must mean that 1 equals 1 over 1 squared, which it does. Okay, let's go ahead and write our sequence as an explicit number. Well, we know there's a 1 on top. And the bottom is something squared, because the squareds go out throughout the whole thing. Well, I have 1 squared for my first term, so that means that's just going to be n squared. Because when I plug 1 in for n, yep, I get 1 squared. When I plug 2 in for n, I got 2 squared for my second term, so we're good. And then we just have to write our sigma notation. I'm going to start at 1 again. Where do I end this time? I end at infinity. So we're just going to put the infinity sign up there. And we're just going to say 1 over n squared, and we are done. The last thing we're going to talk about is changing indexes. We're going to go ahead and change indexes. And what this means is if they give me, my very first one is 2. I'm going to start at 2, and I'm going to 6. Not in this class, but in other classes, you need to start at the exact same place to be able to compare two summation formulas. So we have to get down how I can change this to anything I wanted to. I can actually change this number to any number I want to, and it will keep this summation the exact same. So we're going from 2 to 6 right now. So let's just see what that looks like when I actually do the summation. So this is going to become 2 plus 3 plus 4 plus 5 plus 6, because every one of these I just replace I with it. So I replace I with 2, with 3, with 4, with 5, and with 6. So my directions say I need to change that index from 2 to 1. So I need to have on the bottom I need to have my summation. And we're going to change it to j equals 1. And when I put an equal to sign, I want it to stay this exact same way. So we can't go to 6 because we have 5 terms, 1, 2, 3, 4, 5. So instead of going to 6, if I change this, if I adjust it down 1, I need to adjust this one down 1 as well. So that's going to be 5. So this is 2 minus 1, so that means we're going to do 6 minus 1. If I just left everything as is, don't write this because this is wrong. If I left everything as is, and I start at 1 and I go to 5, this would just become 1 plus 2 plus 3 plus 4 plus 5. Do those two sums equal? Nope, so that doesn't work. We have to do something with that I. What do we have to do with that I? Like I called you 4 times today. I'm going to pick someone new. Chris.
Could we have an I plus 1?
We can have an I plus 1. So rather than having I, we're going to replace that I with I plus 1. Well, that means we're going to have 1 plus 1 plus 2 plus 1 plus 3 plus 1 plus 4 plus 1, and finally plus 5 plus 1, which is going to give me that 2 plus 3 plus 4 plus 5 plus 6 that we had above there. So what I put in my notes here, how exactly did I word it? I went ahead and I just put if adjusting down 1. So if we adjust down 1, if adjusting down 1, so I'm going down value, I am going to replace I with I plus 1. So if I subtract 1 from here and here, I have to add it back in here. All right, it kind of cancels each other out. Right? If I add and then subtract, it keeps everything the same. So the same thing's happening here. If I subtract a value here, I'm going to add it over here. So if adjusting down, replace it with I plus whatever you're adjusting down by. All right, for our next example, I need to go from I equals 3 to I equals 1. Well, that means I'm adjusting down 2. So that means I need to adjust my top by 2 as well. What's infinity minus 2? Still infinity. So that doesn't actually change anything. That's an 8. That's an infinity. So infinity minus 2 is still infinity. So we don't change the top if it's infinity. Well, this time I adjusted down 2. So this time I'm going to replace my I with I plus 2. And we're going to square, and we're going to be careful to make sure we put our parentheses correctly. It's the whole quantity squared. And if you ever want to check to make sure you did it correct, just check your very first term. This very first term would be a 3 in for this I, so it would be 9 on the bottom. It would be 3 squared. Well, if I plug a 1 in here, I had 1 plus 2, which gives me that 3 again, 3 squared. So that is correct. So if I adjust down 2, I just add 2 to all of my i's. All right, to every I that we have. All right, that last one. I need to rewrite this as I equals 1. Well, this time rather than going down, I'm adjusting up. I'm going from -1 to a +1, so I'm adding 2. I'm adding 2, so that means on the top I need to add 2, so my new top is going to be 7. 5 plus 2 gives me that 7. So if I adjust down, I have to add. What do you think happens if I adjust up? Lewis, what do you got? I'm going to subtract. So if I subtract 2 off of these, or add 2 to those, we are going to replace all of our i's with I minus 2. And we're going to replace our other I with I minus 2 plus 1. Let's just double check that everything worked out. So if I plugged a -1 in for each of these i's, I'd have -1 for both those i's. If I plug 1 in for here, I have 1 minus 2, which is a -1, -1. Everything stayed the same. So once again, I'm going to put if adjusting up to. So if we're adjusting up, we're going to replace I with I minus 2. So just remember to keep it balanced. What I do here, I have to do the opposite here. So if I'm subtracting 2 from my I have to add 2 back in. If I'm adding 2 to my I have to, or from here, I'm going to subtract 2 from my I. And don't forget about your endpoint. All right, it's the easiest thing to forget about. So if I adjust up here, I have to adjust up here as well. All right, any questions, comments, or concerns? So that's the long and short of sigma notation. This homework is straight out of the book, so you can check your answers on the normal answer guide. Remember that test corrections are due Friday, and if you haven't already, please take that survey. All right.